The crate in this problem is pushed along a rough horizontal floor. It's pushed by a force P from the worker, and it moves at the constant speed of 3.5 meters per second. We're asked in Part A to find how hard the worker has to push it. We're asked to find P. Let's start doing this by drawing the crate's free body diagram. The crate's weight is directed straight down. The normal force acting on it is straight up, perpendicular to the surface. The worker pushes to the right, and kinetic friction opposes the motion, so it's directed left. Now we can apply Newton's second law, summing the forces in the x direction, setting it equal to mass times acceleration in that direction, and the same thing for the y direction. We can write these equations in either order. Let's start with the y component. We read the sum of the forces from the free body diagram. Normal force is in the positive y direction, minus the weight. And the crate has no acceleration in the y direction. It's moving horizontally, so AY is 0. And we find that in this case the normal force equals mg. Let's look at Newton's second law in the x direction now. There are two horizontal forces. The pushing force is along positive x, and kinetic friction is along negative x. The crate moves in the same direction at a constant speed, so its acceleration in the x direction is 0. This means that the worker must push with a force the same magnitude as kinetic friction. And remember that kinetic friction always has the magnitude mu sub k times n, where mu is the coefficient of kinetic friction. In our case, n equals mg, so we can substitute that and calculate, finding that the worker has to push with a force of 33 newtons to keep the crate moving at a constant speed. Part B asks us how far the crate would slide if the worker suddenly stopped pushing it. So we're asked to find this distance d for the crate to stop if the pushing force is 0. Let's first redraw the free body diagram for the case where the pushing force P equals 0. And all that does is remove that force, so that when we sum forces in the x direction, we only have friction pointing along negative x. So we have minus F sub k, minus the force of kinetic friction, equals mass times acceleration. That tells us that the acceleration is negative the magnitude of the friction force divided by the mass. Substitute kinetic friction force equals mu sub k times n, where n in our case is mg, and cancel the m's to see that the acceleration is minus the coefficient of friction times g. That works out to minus 2 meters per second. The negative there tells you that the acceleration is in the negative x direction, which is towards the left. Knowing this acceleration, we can use kinematics to find the distance that the crate moves. The initial x component of velocity for the crate is 3.5 meters per second, and the crate moves a distance d before its final velocity is 0. Let's write the time-independent kinematic equation, where delta x, the displacement, is d, the final velocity is 0. And solve this equation for the distance that it moves, d. It's minus v naught squared over twice the acceleration. Substitute the values and calculate to see that the crate moves 3.1 meters to the right before it stops.